So, hey everyone, welcome all at our weekly seminar at Jagiellonian. It's just before a long weekend in Poland. Tomorrow we have Independence Day. So for most of us, it's the last work-related activity. And we are really happy to have a distinguished guest from Charles University, Zdeněk Dvořák. So I know Zdeněk mostly for his activity in the structural graph theory business, also graph colorings a lot. I always admired his diversity in the research tools and interests. So he's not afraid of discharging method. He does lots. I've seen lots of variants of graph minor structure theorem that he was building for his results. And lots of nice stuff about sparsity business. So weak coloring numbers is one of the topics, and others. So today, as we discussed, he's going to speak about something new to him, or new, and yeah, welcome, Zdeněk, and the floor is yours.
Okay, thank you for the introduction and for inviting me. So I will be speaking about some results about asymptotic dimension, and these are actually quite new results, which we obtained with Sergey when I visited him a couple of weeks ago. So let me start with some introduction. As Piotr said, I'm mostly interested in structural graph theory and graph coloring. So let's see how this concept of asymptotic dimension fits into that. So let's start with a coloring, and let's start with a definition of a proper coloring, which is needlessly complicated, but it will help us to define other things. So let's consider some assignment of colors to vertices of a graph, and a monochromatic component is just a maximal connected induced subgraph where every vertex has the same color. And now we say that this function is a proper coloring if actually each monochromatic component is just a single vertex. So this is a weird way how to define a proper coloring, but it's sure it works. And the chromatic number of a graph is then the minimum number of colors that you need to properly color your graph. And I mean, the reason why I have defined the chromatic number in this strange way is that now we can play with this definition and replace this being a single vertex by other conditions, and we get some other variants of graph colorings. And one of the most natural ones, most interesting ones, is the notion of clustered coloring, where you consider some fixed integer s, and you say that this assignment of colors to vertices is an s-clustered coloring if each monochromatic component has size at most s. So being one clustered means that each monochromatic component is just single vertex, so it's just a proper coloring. But if we allow like bigger bunches of colors, bigger clusters of colors, we can get we can color more graphs using the same number of colors. And so if you fix this size s of the clusters, you can define this chromatic number with clustering s, which is the minimum number of colors that you need to get such a coloring. And I mean, like this notion is kind of maybe not so interesting for a single graph, because for a single graph, you can, if you take s to be larger than the number of vertices of the graph, then you can just use one color. You still can get some interesting results when you really fix s to be some particular value, but since we are kind of rather more interested in like things qualitatively, it's more natural to consider the clustered coloring for graph classes. And so we will define a this clustered chromatic number of a class of graphs to be the minimum number of colors, such that you can fix some size of the clusters so that every graph from this class has a coloring with clustering at most S using at most C colors. So let me give an example. So clearly you can color every cycle using 2 colors, so that each monochromatic component has size at most 2. And therefore, if you take the class of all cycles, it will have clustered chromatic number 2. So this was kind of a trivial example. I will speak in a moment about like more interesting results about clustered coloring. But before we do that, let me mention that as usual, as you can do basically for every variant of graph coloring, you can also consider the list version of the notion. So instead of choosing each color of each vertex from some fixed set of colors, each vertex can have its own set of colors from which you have to choose from which you have to choose. And so more precisely, a list assignment is a function that to every vertex assigns some set of allowed colors that you can use at this vertex. A coloring is an L coloring if the color of each vertex belongs to its list. And then kind of the standard definition of in this context is the list chromatic number or choosability of a graph, which is the minimum C, such that every such that this graph G has a proper coloring from every assignment of lists of size at least C. And then, of course, you can do the same thing with this clustered chromatic number. So well, I probably don't have to go into details. Okay, so let's go to the results. So this is some not entirely random selection of some results of on clustered coloring. So there are, of course, many other known results about this topic. And if you are interested, David Wood has written a very nice survey where he goes over a lot of them. But let's see what we have on the slide. So if you take the planar graphs and you allow yourself to use clusters of colors, then you actually don't get anything new. We know that all planar graphs are properly four-colorable, and even if you allow yourself to use larger clusters, you cannot do it better. There are planar graphs that require 4 colors. But you can do slightly better when you go to the list version. In the list version, there are planar graphs which have choosability 5, but all planar graphs have clustered choosability at most 4. And when we are considering planar graphs, we can do something which I like quite a bit, and is to consider the triangle-free case. there is this famous result of Grech that every planar triangle-free graph is recolorable. And again, it turns out that even in the clustered setting, you cannot do better. You cannot do just two coloring for planar triangle-free graphs. But again, you at least win a bit in the list coloring setting because normally you need their list of size 4. In the clustered version, it's list of size 3. And finally, let me mention results on KT minor free graphs. So, of course, there is Hadwiger's conjecture, which tells you that KT minor free graphs should be T-1 colorable, but we are, of course, nowhere near to be able to prove it. But here the situation in the clustered coloring setting is much better. So, in fact, we are able to prove this clustered version of Hadwiger's conjecture, except that our paper with Sergey hasn't been finished yet. So, and it hasn't been finished yet for a couple of years, and it probably won't be finished yet for a couple more years. So you may have some doubts about it, but I think like the best result which is published is that at most T+1 colors are certainly enough. Okay, there are two things on this that are worth mentioning. Is that actually in this setting there is not much difference between planar graphs and graphs that can be drawn on any fixed surface. So all the numbers stay the same, when instead of planar graphs, I consider the graphs drawn on the torus or any other fixed surface. So that's very different behavior from the, let's say, the ordinary coloring, where the chromatic number is, let's say, roughly square root of the genus of the surface. Here it stays constant. And secondly, a lot of things become easier or better if you bound the maximum degree. So, for instance, in the planar case, in the case of graphs drawn in the surface, you in general need 4 colors, but if you bound to the maximum degree, 3 colors are enough. And for these classes where you actually this holds in much greater generality, even if you just take a class of graphs that forbid any fixed minor and bound the maximum degree, then 3 colors will suffice. And as you can see, this very general result actually comes from this paper by Chun-Hun Liu about asymptotic dimension of minor closed classes. So you'll see that there will be some connection to the topic of my talk. So let me mention like a couple of open questions on this slides. For planar graphs on surface which are triangle free, it was open whether bounding the maximum degree actually helps, whether it helps you to decrease the number of colors that you need from 3 to 2. And also the results that we have for graphs on surfaces for bounded maximum degree are specific to proper coloring, so it's not clear what happens in the list coloring setting. And the results that I want to report on my talk is that actually in both of these settings the answer is yes. So this whether, let's say, planar triangle-free graphs of bounded maximum degree have clustered chromatic number 2. This was asked or conjectured by Espere and Jaurès, and this question for the list chromatic number was asked by David Wood in his survey. Okay, so actually we will give the results in greater generality, which also moves us closer to the topic of the asymptotic dimension. We will give them in the setting of weak diameter coloring. So what is a weak diameter coloring? So what is a weak diameter? So suppose that I have some graph G, and inside it I have some subgraph C. Well, then the weak diameter of this subgraph is the maximum distance between the vertices of C, but the distance is measured not inside this subgraph C, but in the whole graph. So in particular, if, for example, this graph contains a universal vertex, then the weak diameter of anything is at most 2. And now a weak diameter for some fixed integer s, a weak diameter s coloring is just what you get from this strange definition of coloring that we started with. If the restriction that you give on the monochromatic components is that they must have weak diameter at most s. So this is still some generalization of a proper coloring, because if you take S being 0, weak diameter being 0 just means that each monochromatic component is a single vertex with just a proper coloring. And well, now as usual, let's let this denote the minimum number of colors that you need to use if weak monochromatic components have size at most S. And let me mention that, let's say, unlike the clustered coloring, this parameter is well, somewhat well, maybe less well behaved. For example, in the sense that it is not monotone, that deleting the vertices from your graph can increase this chromatic number. So if if the graph has a universal vertex, and as I have said, everything has weak diameter at most 2, so you just need one color to color it. But if you delete this universal vertex, suddenly you may need a lot more colors. And then, as we did with the clustered coloring, we can define naturally this weak diameter chromatic number of a graph class by taking the minimum color such that all graphs from this class can be colored using this number of colors, so that the weak diameters of monochromatic components are at most some fixed number S, which is the same for the whole graph class. And we can define the list version of this concept. And there are some obvious connections between the clustered and weak diameter coloring. So on one side, the weak diameter chromatic number is always at most as large as the clustered chromatic number, because if each monochromatic component has size at most S, then this component has diameter and therefore also the weak diameter at most S-1, so it's also bounded. And on the other hand, if the class of graphs that we consider has bounded maximum degree, then these two parameters coincide. Because now, if something has bounded weak diameter at most S, So it means that it's all contained within distance, well, at most s from some vertex of the graph, and now this ball of diameter of radius s can have at most delta to s vertices, so it has bounded size. And so actually the results that we have are for this big diameter coloring. So we prove that if you have a graph drawn on a surface which is triangle free, then it has weak diameter, chromatic number at most 2, and actually even in the list coloring setting. And without this assumption that it's triangle free, it has this should be list version. So this is wrong. This should be this. And the same is true for the list version when considered for any fixed surface. And let me mention maybe one more result that I will actually get more into the later in my talk. We also get a bound on the weak chromatic number of intersection graphs of fat objects in fixed d-dimensional space. By fat objects, you can, for example, imagine balls. And so I think that this is actually kind of an interesting connection, which maybe a little bit explains why clustered coloring sometimes behaves better when you bound the maximum degree, because maybe at that point it actually becomes the same as this weak diameter coloring, which then maybe is easier to work with or nicer behave. Before I get to this argument, let me actually go to even greater generality and speak about asymptotic dimension. So, what is an asymptotic dimension? So let's start. What is a dimension of some, let's say, a metric space? And well, there are different definitions, but the one that is kind of relevant or motivating for the notion that we consider is this Lebesgue covering dimension, which says that a space has dimension at most d if you can get arbitrary fine covers such that which have thickness at most d+1. And by thickness, I mean that every point belongs to at most d+1 elements of the cover. So for example, why a line has dimension 1? Well, that's because I can cover it arbitrarily, finally, by some sets such that every point belongs to at most 2 of them. Why the plane has dimension 2? Well, because I can cover it by some things like this, and if I'm careful enough, every point will belong to at most 3 of them. And the way this Lebesgue covering dimension works is that it kind of works on small scale. So I want this to be the case if I have a look at arbitrarily small scale, which kind of is what, in a sense, one expects for the dimension. One expects that if you take your line, but somewhere on it you attach a small plane, it will still have dimension 2 because you have attached this plane here. But it's not always what we desire. Sometimes, and in particular, let's say in the structural graph theory, what we kind of want to look at is like the large scale behavior, large scale structure of the graphs that we consider. And in that case, I mean, we don't want this dimension to be spoiled by some things which happen on the local level. I mean, in some sense, if I take a bunch of squares and a lot of squares and connect them, or infinitely many squares, and connect them one after another in some such path-like manner, then on the global level, this behaves like it's a one-dimensional object, not two-dimensional one. And motivated by some ideas like these, Gromov defined the asymptotic dimension, which is kind of a dual to this Lebesgue dimension, which instead of looking at arbitrarily fine covers looks at like coarse covers. So the asymptotic dimension of a space is defined as being at most D if whenever you give me a cover of the space where all the elements of the cover have bounded size, uniformly bounded size, you will be able to give a coarser cover, by which I mean that each of these sets from the starting cover must be contained in at least one of the sets of the resulting one, which is still uniformly bounded. These still must have bounded size, and additionally have this property that every point belongs just to few of them. And now armed with this definition, we can move on to the graphs. Of course, this definition, as it's set here, doesn't make much sense for any finite graph. I mean, for if you take the metric space of any finite graph, it will have asymptotic dimension 0 because well, you can just always put everything in a single bed. I mean, any bounded metric space has this asymptotic dimension 0. So of course, you could either work now with infinite graphs, which I don't do, or you can work with classes of finite graphs. And so we can define the asymptotic dimension of a graph class as follows. So we say that it's at most D if there exists some function such that the following claim holds. So for every R, which will be like the sizes of these sets in this starting cover from this definition, and there must exist a cover of the vertex set of the graph such that all the R balls, all the sets of radius R are contained in at least one of the parts. I mean, we could write it here with some arbitrary cover, but we can just consider the cover consisting of all the R balls of our graph. So each of them must be contained in at least one set of this cover. This cover must be bounded. So each set of the cover must have bounded weak diameter, well, it has to have weak diameter at most this function of R. And it must have this property that every vertex belongs to at most d+1 parts of this cover. So this is just a direct transformation of this definition of Gromov to the graph setting. We can play with it a little bit. So one way how to play with it is that instead of considering covers, you can consider partitions of the vertices of your graph. And how you do that is that you imagine you have this cover, and now you shrink every set by R. So remove from every set everything which is a distance R from its boundary or whatever. This in the resulting thing, every point will still be covered because every ball of diameter R is within one of these sets. So if I shrink this set by R, its center still stays within the part. And well, now these things, the sets would still overlap, but let's remove the overlaps. Let's just consider the partition. And so you will, in this way, you will get a partition which, I mean, these parts have bounded size. And now it has the property that every vertex, the ball of radius R around every vertex intersects at most d+1 parts from the partition. And it turns out you can simplify this even more. I mean, this step from the original definition to here is kind of trivial. Then comes a very non-trivial step, or I mean, that's the step that I don't quite understand why it works yet. I mean, I have seen the proof. I trust the proof. I don't see why it works. You can so how can you enforce this property that every point is close to just few parts of this partition? Well, you can do it in the following way. So your partition should be divided into d+1 disjoint subsets, and in each of them, let's say in P1, the distinct parts that you put into this set should be far apart, a distance greater than R. Or, I mean, to match with this previous definition, I should put, I guess, greater than 2R, but qualitatively it doesn't matter. So what this means that if I, let's say, have a look at these parts which are in this P1, any vertex can be close to at most one of them, because if this distance is at most R and the distance between any two sets is greater than 2R, I obviously can't also intersect this one, or the ball of radius R and LB cannot intersect this one. So if I have a system of partition which I can divide into these d+1 parts with this property, then it obviously implies the previous version of the definition.
Zdeněk, can I have a question?
Yes.
A vertex can be also far away from a single part, right? What you keep is that there is a part that it's close to, but from P1 it could be very far away. Is it true? Yeah.
It could. There might be some vertices where the ball of radius R here do not intersect the P1 at all.
Okay. Yeah. Okay. Thanks.
Yeah, but altogether this should be the partition of the whole vertex set. So every vertex belongs to one of the parts.
Okay. Thank you. Mm-hmm.
And kind of the magic thing is that actually these two definitions are equivalent. The fact that this one implies the previous one is obvious, but somehow it works in the other way as well. And so this is the definition that we will be using, because in this definition it has a direct connection to the weak coloring numbers. So I can just imagine that these are colors. So I will give all the vertices which are in the parts of P1 the color 1, all the vertices that are in the parts of P2 the color 2, and so on. And so what just happened? So if I have a look, so let's fix this radius r somehow. So if I have a look at the r's distance power of my graph, I join any two vertices which are at a distance r from one another by an edge, I will not have any edge between different parts. So each monochromatic component of this coloring must be contained strictly within this part, and therefore each monochromatic component must have size at most f of r. And well, therefore, given this, I am getting a weak diameter coloring using D+1 colors. And conversely, if I have weak diameter coloring of this R's power by D+1 colors, I can just take the parts to be the monochromatic components and I'm getting here. So this definition just tells me that a graph class has asymptotic dimension at most D if for every integer r, the class of the r distance powers has weak chromatic number at most D+1. And I mean, so in particular, all these results on the asymptotic dimension have as a special case that, so if you show that a class G has asymptotic dimension at most D, then as a special case for R equals 1, this just implies that the class of graphs has weak diameter chromatic number at most D+1. And so what Junhon actually proved is not just these results about the weak diameter coloring or clustered chromatic number, but he proved these nice results that, I mean, all if you take class of graphs drawn on a fixed surface, it will have asymptotic dimension 2, which is like really what you would want. You really want surfaces in this sense to have asymptotic dimension 2. He also proved that all classes where you forbid some minor have asymptotic dimension 2. So in this sense, they are very close to being surfaces, as you would kind of expect from the structure theorem. He also proved that classes of bounded tree width have asymptotic dimension 1, so they behave one-dimensionally. And okay, and our proof here I've mentioned this result on the weak diameter coloring of intersection graph of fat objects. We actually carried it out also in this asymptotic dimension setting. Okay, So let me speak a bit about these results that we got. So kind of you could view these results like answering or trying to approach to kind of natural questions. One of them is, what is this about the graph class that causes its asymptotic dimension to be large? Can we get some kind of qualitative answer to this question? And the other thing is whether geometric graphs have bounded asymptotic dimension. You would imagine that this could be the case for a good definition of a dimension, and so that's something that you are interested in. And I mean, for the first question, you might kind of suspect that inside any class which has, let's say, asymptotic dimension at least d, you might be able to find some representation of some canonical thing of dimension d, such as d-dimensional space. I mean, I don't need to know what this means. It doesn't mean anything, but I mean, some vague idea like this, and it doesn't seem to be as easy as this, but I mean, as simple as this, that we could say something like this, but yeah, we were not really able to say anything reasonable about this, even in kind of like the first non-trivial case of the dimension being 2. So you can try to simplify things, to try to think about what causes an asymptotic dimension of some subclass of planar graphs. To well, which subclasses of planar graphs have asymptotic dimension 1, which have dimension 2, which are like kind of full dimensional within the planar graphs. And that seems still like fairly complicated question. So you can have a look at like this very basic case for the asymptotic dimension. So what happens at distance 1? So what happens at weak diameter coloring? So which classes of subclasses of planar graphs have a weak chromatic number 2, which have weak chromatic number 3. And for that, there is actually kind of, we have kind of feeling that this might be answerable. We don't have an answer. We tried, we weren't able to make it quite work, but here is kind of an idea. So what certainly is true, that if in your planar graph you happen to have a cycle where this left part is far from the right part, and this top part is far from the bottom part, and the interior is triangulated, then you cannot get a weak diameter coloring using 2 colors, because of the so-called hex lemma. In any 2 coloring of this, let's say by colors blue and green, you will either have a blue part connecting the left side with the right side, or a green part connected the top with the bottom. And so in this way, you will always get a monochromatic component which has large weak diameter, because we assume that this left part and the right part is far apart. They are far apart. So this is a reason why you might not be able to get a coloring by 2 colors. And we suspect that it might, in some sense, be the right answer. So in particular, here is our, well, okay, I will be brave. I will call it a conjecture. So let this G of B be the class of plane graph. Oh yeah, can be drawn. Okay, yeah. This is class of graphs that can be drawn in the plane, such that every vertex is at distance at most b from some long face, from a face which is not a triangle. So this is something which doesn't happen in this graph here. If we have a look at the vertexes which is in the middle of this triangulated thing, it will be far from a non-triangular face. And let's also assume that there are no separating triangles. I mean, it could be that inside I have here such a triangulated thing, and then inside each triangle I add another planar graph which contains a fourth face, and it obviously doesn't help. So, and then our conjecture is that this class of graphs has weak diameter coloring by two colors. We don't, we can't prove this. We can't prove this even for this class G0, which are planar graphs where every vertex is incident with some long face, but it can have, there can be some additional triangular faces. What we can at least prove is even a simpler version, where the graph is actually triangle free. So all the faces have lengths at least 4. And this answers this conjecture of Espere and Jaurès, who conjectured it for the clustered chromatic number of planar triangle free graphs. And okay, let me speak a little bit about and using the very same method, we can show the bound of 3 colors for graphs on surface. Let me speak a little bit about the method that we use. So there is this quite general result that we have with Sergey that tells you that if our graph is, let's say, from some proper minor closed class, so avoids fixed minor. Actually, it's more general, but let's stick with this. And all of its subgraphs are fairly sparse. So the number of edges inside any subgraph is at most C minus epsilon times the number of vertices, plus maybe some error there. Then you will be able to get a clustered coloring by at most C colors, or in fact clustered choosability at most C. And this is by so-called island argument. I don't really want to go into details. It's not very important here. So, in particular, if it were true that for planar triangle-free graphs, we have that the number of edges of a planar triangle-free graph is at most 1.99 times the number of its vertices, then plus whatever, then we would be good. It would imply that we can color them. We get a clustered coloring using 2 colors, but it's not the case. If you take planar triangle-free graphs, the best you can get in general is that they have at most twice the number of twice n edges. But this is kind of very close. If we can make them a little bit sparser, this theorem will apply. And the way how we make them sparser is that we delete some things from them. So in particular, it turns out that that you can make these graphs sparser if you delete vertices of degree 3 and cycles, 4 cycles formed by vertices of degree 4. So here is some claim about elimination of 4 cycles. So that so if you delete from your graph a bunch of disjoint non-adjacent 4 cycles where their vertices have degree 4, and then you are able to color the rest of the graph using 2 colors with bounded weak diameter, then you will be able to color the whole graph at the expense of making the weak diameter a little bit larger by adding at most 6. And how you can do that, you would probably work it out for yourself. You need to be a little bit careful in the extension so that you do not, let's say, connect 2 existing monochromatic components into a larger one, or increase its radius, increase its diameter too much. But let's say if the neighborhood of this looks like this, you could color these 2 vertices red and sorry, not red, these 2 vertices blue, and these 2 vertices red, and you see that from this red component you only got here and increased its diameter by here at most 2, and in the blue one you get here like this. And then you need to work out a couple more cases of how the neighborhood of this 4 cycle can be colored. And you can always do it increasing the weak diameter by at most 3 inside each of the 4 cycles. And because the 4 cycles are non-adjacent, this increases the weak diameter of any component by at most 6.
Sorry, Zdeněk, can you go back to the previous slide?
Yep.
All right. So, but this theorem is about clustered coloring, not the weak distance coloring, right?
Yeah, but of course this
okay.
Also implies that
sure.
weak diameter coloring is at most this.
Okay, perfect.
Yeah. I mean, yeah. So this is this claim here is. Here it is now important that we work with weak diameter coloring. I mean, this doesn't help you with the clustering, because now the clusters can get a bit large.
Okay, thank you.
Okay, and now there are some technical details which I will skip because I'm speaking for long enough. Basically, what you show is that if you like delete a maximal independent set of these vertices of degree at most 3 and 4 cycles, then you will get a graph which is substantially sparser. That's just by standard discharging argument. You need to be careful that actually this density result also holds for a subgraph. So it's not the case that now if I go to a proper subgraph, I will again get 4 cycles of vertices of degree 4 or vertices of degree at most 3, which takes some work. You need to play with forbidding separating 4 cycles, and then you need to handle the separating 4 cycles by some recurring extension arguments, but let me not go to the details. I think that these two things are like the basic ideas that we use there. And let me also mention that it's important that we work with the weak diameter. You could be tempted to try to make the proof work for the diameter of the components rather than like where you measure the distance within the component, not inside the graph, but that doesn't work. There are actually counterexamples showing that you cannot do it. You cannot, let's say, two-color triangle-free graphs such that all the components have bounded diameter. Okay, let's me now speak about our second result, which is about geometric graphs. And I mean, the geometric things should have bounded dimension. That seems kind of, if you have a geometric graph in d-dimensional space, you would expect its dimension to be something like d. That's not always the case. I mean, it's fairly easy to argue that that expanders with bounded maximum degree have unbounded asymptotic dimension, and there are some geometric graphs in some fairly natural geometric graphs which enable you to represent expanders. So, for example, if you take touching graphs of axis-aligned boxes in 3 dimensions, you will be able to represent arbitrarily large subcubic expanders in this way, and therefore, let's say the touching graphs of axis-aligned boxes in 3-dimensional space have unbounded asymptotic dimension. But at least we were able to show bound on a dimension for fat object. So what I mean by a fat object, it's a object in in this d-dimensional space, where if you have a look at any point in this object and you have a look at ball of radius r around this object, which is reasonably small compared to the diameter of this whole set A, then the volume of our object that falls into this ball is reasonably large, grows like this. So this kind of forbids things like well, extremely long and thin objects, where although we live in 2-dimensional space, I mean this volume here behaves 1-dimensionally. And examples of things which have this property are things like balls and hypercubes and things like that. And then if you have an intersection graph of such a system of fat connected objects in d-dimensional space, it will have asymptotic dimension at most 2d+1. So this gives at least some like justification for this intuition that geometric graphs in bounded dimension should have bounded asymptotic dimension. And how do we prove this? I will not go much into the proof. What we do is we find that such graphs you can decompose their vertices into d+1 parts, such that each part induces something like a graph of small treeways. It's not a graph of small treeways, it's something more general. We also need to take actually these R's powers of the graph, not just the graph itself. But basically, if you view it like that, each of these parts induces a graph of bounded treeways, it will give you a good initial intuition. And then we use the result of that graphs of bounded treeways, or this generalization of graph of bounded treeways, has asymptotic dimension 1. So you can color them using 2 colors. So you spend 2 colors for each of these parts. So you will have 2D plus 2 colors in total, which means that you will be getting asymptotic dimension 2D plus 1. And things are technical, and I will skip them. Let me finish the talk with mentioning some open questions. So I have already spoken about this conjecture, which we think that solving it would give a lot of insight into the asymptotic dimension of planar graphs. Also, for these geometric graphs, we were able to show the asymptotic dimension 2D plus 1, which was because we split into D plus 1 part, and on each of them we needed to use 2 colors. But it feels kind of wrong. I mean, it feels that maybe these objects should have actually asymptotic dimension D. I don't know why. It's just, I mean, it would be aesthetically pleasing, and this might be complete nonsense. I don't really have that much insight into either asymptotic dimension or intersection graphs that I would claim this to be the case with any certainty, but it certainly would be nice. And let me mention one last problem, which is actually from this paper by there was this paper by Chunhoon, and then another paper by a larger group of authors, and they made actually joint paper where they have a lot of further interesting results. And in particular, in this paper, they mention these questions, whether it is true if you take a, I guess I should have put here hereditary classes of graphs with strongly sublinear separators have bounded asymptotic dimension. And if that were the case, that would be quite nice, because I mean, things that don't have small separators are expanders, and we know that the bounded degree expanders have large asymptotic dimensions. So that would be kind of an interesting duality there going on. Okay, thank you for your attention.